Okay, this is a continuation in a series of videos whose express purpose is to show you how to solve various kinematic problems effectively and, most importantly, quickly using the SUVAT method. Now, I am assuming that you have seen part 1 video, which is the introductory video, and if you haven't done so, I would encourage you to do that. In it, I explained various kinematic concepts and discuss the merit and the rationale behind the SUVAT method, and also review physics terminology that is often confusing to students and equation derivations of the kinematic equations in detail. So I'm just going to scroll very quickly through this. If you want to pause to look at the introductory video's contents, you can. Okay. So just to review, the way to recognize that you're dealing with a kinematic problem is first you want to identify that the object is under constant or uniform acceleration or deceleration, and that you're also given enough information regarding the SUVAT, displacement, velocity initial or final, and time. So you're not going to be dealing with anything regarding forces, so you won't be looking to work with newtons or kilograms or mechanical energy like potential energy or kinetic energy, so you won't be dealing with joules. So none of that. The 4 steps of the kinematic of the SUVAT method is: 1. You write SUVAT vertically. 2. You enter 3 out of the 5 SUVAT variables next to their letter. 3. You circle the variable that you need, and 4. Draw an arrow through the variable that is left and use the equation that's affiliated with that variable to solve for the circled variable in 3. So when you're about to get the solution to your question, kinematic question, you should have something that looks like this. 3 bits of data, 3 out of the 5. You've circled the one that you need, and you've drawn a line through the one that's left, the variable that's left, and you have the affiliated equation with that letter T, for example here, and that is how you quickly find the one and only one of the 5 equations that can be used in a SUVAT problem, in a kinematic problem. That's if you only get 3 bits of data. That's how you will find it fast. And these are all the equations that are affiliated with the missing variables. Presumably you understand this table by now. So just to remind you that the SUVAT method is essentially like a simple algorithm that quickly directs you to the one and only equation that you need. Alright, so let's get to the first problem here we're going to do. And it's a good problem. Kind of different in traveling the 70 centimeters along a rifle barrel. A bullet uniformly accelerates from rest to a velocity of 210 meters per second. Find the acceleration involved and the time taken for which the bullet is in the barrel. Okay, so we'll deal with the first part of the question, find the acceleration involved. So first of all, we want to make sure we're dealing with the kinematic problem. Well, we've got a bullet that's traveling uniformly in a uniform acceleration from rest, so it's sitting here in the beginning of the barrel at rest, and when it comes out the end of the barrel, right at the moment it leaves the end of the barrel, it's got a velocity of 210 meters per second. So we've got 0 meters per second here, and we've got at the end of the barrel there. So we've got 2 bits of information. We've got uniform acceleration, and we also have a displacement of that bullet. It's 70 centimeters. Now, one thing we've got to do is we've got to realize that we're working with meters, kilogram, second, the MCAT system of measurement when we do our physics problems, unless shown otherwise. But we're going to be using the MCAT, so we can't use centimeters. We have to convert to meters. So we just use our conversion factor here. 1 meter is equal to 100 centimeters, so that if we take this ratio and put it in a way where the units centimeters cancel out, we find that we have to divide 70 by 100, knock out a couple zeros, we got 7 over 10, and we end up with meters as being our only unit left. So we end up with 0.7 meters as this value here. Okay, so now we've got 3 bits of information and we're ready to row. So we have here 0 meters per second. Let's get a little more organized here. We got step 1 where we write our SUVAT. Step 2, we enter 3 bits of information. We've got our initial velocity of 0 meters per second. We got our final velocity of 210 meters per second. We've got our displacement in the barrel, which is 0.7 meters. That's step 2. Step 3, we circle the variable that we're looking for, and here we're looking for the acceleration, so we'll circle that. We draw a line through the step 4, we draw a line through the variable that's left, and we write the affiliated equation with that with this variable here, and that happens to be final velocity squared is equal to initial velocity squared plus 2as. Okay, so now we're done with the hard part of the problem. We come down here. I filled in the data again, and so we take our equation here and we plug in the information that we have. We've got v, we've 210 meters per second squared. We got u, 0 meters per second. I'm saying 210 meters per second is v, u is 0 meters per second. S, our displacement is 0.7. We're solving for a. We do the math, move things algebraically around, and we end up with, after we do that, and I'm assuming that you can follow the math here, pause the video if you need to. So we end up with that. Now I want to just address these units here, because we always want to put our units in our problem to make sure that when they do cancel, we end up with the right units. We're looking for acceleration, so we should end up with meters per second squared. Okay, so we just want to make sure that we have the right cancellation. So in this situation, we've got meters per second, that's squared, meters per second, seconds squared. So we've got those squared over squared, and then we've got meters on the bottom. And so the meters will cancel on the bottom, one of the meters will cancel on the top, and so we're left with meters per second squared. Okay. I'm going to address how to cancel these out more easily in the next video, but for right now we'll move on. So our answer anyway is, after we did the math, it's 31,500 meters per second squared, which seems like quite an acceleration, and it is. But let's take a look at the second part of the question now. It's the time taken for which the bullet is in the barrel. So we want to know how long this bullet is under this huge acceleration value. Okay, because let me make a point here. I didn't do this in the beginning. Is this gun is got a velocity of the bullet coming out of the barrel of 210 meters per second, and just roughly a meter per second is like 2 miles an hour. It's a little more than that. It's like 2.16 times 2 meters, or 1 meter per second is approximately equal to 2.16 miles per hour. So if we've got, we'll just round it off to 2. If we've got 210 meters per second, that's about, it's over 400 miles an hour. This bullet's coming out. That's really not that fast, actually. There's guns that are higher velocity than that. But anyway, that acceleration is very high. But let's look about how long it takes for that acceleration how long that bullet is under that acceleration. Okay, so we've got this information here from the problem. So now we've got 4 bits of information. Now, in a kinematic problem where you only have 3 out of the 5 bits of information, there's only one equation that you can use. But if you have 4 out of the 5 bits of information, like we do here, then we've got the opposite situation. We've got 4 equations that we can use and only one that we can't. So for example, we're looking for time. The only equation that we can't use is the one that doesn't have t in it. Well, this right here is the missing variable, so we can't use this equation to solve for t, but we can use this one now, this one, or this one. So that's when you have 4 out of 5. The SUVAT is really effective when you only have 3 out of 5 and you have no clue which equation will be the one and only one that you can use. And that's how we did the problem from above. But now we've got 4 to choose from, so the best one would be the easiest one to use mathematically. Now, since acceleration is a fairly big number, I would choose this equation to solve for time because it doesn't have acceleration in it. We don't need it anyway, so we're going to use these smaller numbers here. We'll use these top 3 numbers to solve for t. So we go down here and use that equation. We'll pick this equation here and we'll plug in the information that we have and solve for t. And we've got s, we've got final velocity, we've got u, and we algebraically manipulate things around. So we have meters over meters per second, and the meters cancel and the seconds goes on top. And as you can see, even though we had a tremendous acceleration, 31,000 plus meters per second squared, it's only a very, very short period of time that bullet is under that acceleration. So that's why really this is a fairly low velocity rifle of only, about 400 plus miles an hour. Okay, so let's go on to the next problem here. We've got a choo-choo train uniformly decelerating from 35 meters per second to 21 meters per second over a distance of 350 meters. Calculate the deceleration and the time taken to come to rest from 35 meters per second. Okay, first thing we want to do is make sure that our object here is under continuous acceleration or deceleration, and it says so in the problem. So we've got a kinematic problem here, and we've got bits of information that we can use, 3 bits of information. So step 1 is write SUVAT vertically. Step 2 is fill in 3 out of the 5 bits of information. So we've got initial velocity of 35 meters per second. So it's going at 35 meters per second right here. And then eventually it's going to go down a distance of 350 meters and come at that point, when it's traveled that distance, that at displacement s, our velocity is now going to be 21 meters per second. So we'll put that 21 meters per second. Now that's our final velocity, because at this point our interest in the velocity has ended at the end of 350 meters. And so then we put 350 meters in, and that's step 2. Step 3, we circle the variable that we're looking for, and this one we're calculating the deceleration. Now we don't put d here, we just put a, because acceleration is either if the train is decelerating, that means that if it's going to the right, then the deceleration is going to be to the left. Okay, so we're looking for a acceleration, and it's going to be a negative value because we're just going to arbitrarily say 35 meters per second is positive. We didn't put a negative sign in front of it, and the final velocity is positive. So our acceleration should come out, if we do our math right, should come out to be negative. All right, and step 4 is draw a line through the variable that's left and use the affiliated equation. Again, we're using v squared. Final velocity squared is equal to initial velocity squared plus 2as. All right, so let's look at the math on this. And I just filled in that information here again. So we've got displacement, initial velocity, final velocity. We're going to use this equation. We'll go up here and plug in the information we have. We've got the v, we've got the u, we've got the displacement. We're going to fill all and put your units in. So we've got all our units nicely entered, and we end up with 441 meters squared per second squared minus 1225 meters squared per second squared over 700 meters. Now I want to take some time to show you about the units canceling, because I didn't do that very clearly, I don't think, in the first problem. So we end up with the math of this, and we've got these units like that over that. So what I want to just show you, I've shown this in other videos, is that really when you've got this kind of setup where you've got like the units in the numerator and denominator, you really, the thing to do is to put a line over the meter and put a 1 there. So make it like a fraction over a fraction of units. So you end up with something like this: meters squared per second squared, meters over 1. And I like to think of it as this is like a sandwich. So you've got this 2 pieces of bread here, and the stuff that's in the middle, like that, is on the bottom. So here we've got seconds squared and meters squared. That's on the bottom, meaning the denominator. And the stuff up top, this and this, the stuff that's outside the pieces of bread, so to speak, these lines, is going to be the stuff that's on top. So that's on top, and this is on the bottom, that's on the bottom. Okay, so that means that anything that matches top and bottom can be canceled. So we've got meters. Let me clear this so it's not so confusing. So we've got meters squared and meters, and this is on the bottom and that's on the top, so we can knock that out, and then our second squared is going to still be there on the bottom. So that's how we end up with meters per second squared. And our negative sign persists. Remember, I told you that this train is decelerating, so if we do the math right and we set up all our signs, enter our data right, we'll come out with a negative acceleration, and we did. So the train is decelerating at a minus 1.12 meters per second squared. Okay, now let's just pretend like in the second part of this problem that we're not we found the acceleration, but let's just pretend like we don't know that we've got the same problem with the same information, but that now they're just asking us the time taken to come to rest if we went from this velocity to that velocity in that amount of displacement. So what we're doing is we've got uniform deceleration, so we've got SUVAT, and we're going to write it the letters vertically. We're going to enter our 3 bits of information. Again, we've got 350 meters. We've got an initial velocity of 35 meters per second. We've got a final velocity of 21 meters per second. And this time we're looking for the time taken. So we're going to step 3, circle the variable we need. Step 4, draw a line through the variable that's left. And we end up with the equation affiliated with A, and that's displacement is equal to final velocity plus initial velocity divided by 2 times time. So this is the equation that we're going to plug in now. Pretending like we only have 3 out of the 5. It's the only equation we can use given 3 out of the 5 variables. So we go down here and we put our information in. Oh, let's see what I did here. Oh, you know what I did? My apologies. What I did was I didn't use the displacement. What I did was we didn't use the displacement. I used the initial velocity. My apologies. I used the initial velocity, the final velocity, and then I used the acceleration from the previous problem. So we're just given 3 out of the 5. So the acceleration from the previous problem was minus 1.12, and so I put that in there. So we'll do that. Alright, so we're going to use this and this bit of information, and we are looking for this, and we're going to use that equation, and the equation that's affiliated with that is going to be that right there. Okay, so we put in our final velocity, our initial velocity. We had the acceleration that we calculated from the other problem, we'll pretend like we didn't know what the displacement was. So we have 3 out of the 5 variables, and this would be the only equation we could use if those were the only 3 that we had. So we do the math with that, and we end up with minus 35 meters per second over acceleration here, minus 1.12 meters per second squared. Again, we've got this bit of units that we want to reconcile, and so we look over here, and we've got meters per second over meters per second squared. And again, just pretend like you've got, there's your sandwich, kind of your bread and your sandwich. So the information that's wedged in between is on the bottom. This stuff's on the bottom, and then this and that is on the top. So we've got bottom and top and top. So we're going to cancel out our meters from the top and meters from the bottom, cancel our seconds from the bottom, and one of our seconds from the top is going to cancel. So we're just left with seconds. And that is what we have here, is 31.25 seconds. Notice our signs work out, the negative and the negative cancel out, and our time is positive, which it has to be. Okay, so that's that problem. And then the third problem. A car accelerates uniformly from rest, and after 12 seconds has covered 40 meters. What are its acceleration and its final velocity? Okay, so let's pretend, let's just focus on the acceleration. First, we want to ascertain whether this is a kinematic problem, and it says the car accelerates uniformly, so yes, we've got a kinematic situation here. We've got to find 3 out of the 5 unknowns, which are SUVAT. So what we do is step 1, enter SUVAT vertically. Step 2, enter our information that we do have. Well, we know that 12 seconds has passed. We know that a car accelerates from rest, so we have a 0 meters per second initial velocity and has covered a displacement of 40 meters. So we put that in there. And now we're going, step 3, we're going to circle the thing that we need, and that's acceleration. And then step 4, we're going to draw a line through the variable that's left and write the affiliated equation with it, which is displacement is equal to initial velocity times time plus 1/2 AT squared. Alright, so now we're ready to solve our problem, and we'll go down here and fill in displacement, initial velocity, and then our times that we have, our times. And we do the math, and we find that it ends up being 40 meters equals 72 seconds squared, solving for A. And we end up with meters over seconds squared, which is good because that's what we want. We want acceleration in meters per second squared, and we find that this car is accelerating at 0.56 meters per second squared. Okay, not too much of a acceleration. Now let's just do the same problem and pretend like we don't have the acceleration this time. Okay, so we're just given the same bit of information, but we just were asked what's the final velocity. Okay, so we know it's a SUVAT problem or a kinematic problem because the car is accelerating uniformly. We know that it started from rest. We know that it accelerated for 12 seconds, and we know that in that time period it went a displacement of 40 meters. So that's step 2. Step 3 is circle the variable that we're interested in, and that's the final velocity. Step 4 is draw a line through the remaining variable, which is A, and the affiliated equation with that is this one. Okay, and so we plug in our, so we're solving for V, so we're going to plug in our displacement. We're going to plug in our initial velocity, and then we're going to plug in our time. And we're going to solve for V, and when we do, we find that we end up with 80 meters over 12 seconds, and then we reduce that down to 6.7 meters per second. And that will be the final velocity at this point after it's traveled that displacement with that amount of acceleration. Okay, this is the end of this video. I encourage you to continue working through the other problems if you haven't. I've got several videos before this where I do like 2, 3, sometimes 4 problems in a video. All right, take care.